Tonight, we're going to talk about a possibility so quiet and so clean that it almost doesn't feel scary at first. But the more you sit with it, the more it gets under your skin. The possibility that in a universe containing more stars than grains of sand on every beach on Earth, we might be the only ones here. I don't mean the only advanced civilization, or the only ones with radio telescopes and philosophy and questions about where we came from. I mean only ones in the whole universe. Before we get into this, if you find yourself genuinely surprised by what you're about to hear, take a second to like the video or subscribe. It's a small thing, but it helps this channel reach more curious minds like yours. Now, let's get into it. Most people, when they think about the question of life in the universe, assume the answer is obvious. Of course there's life out there. The universe is enormous. There are hundreds of billions of galaxies, each containing hundreds of billions of stars, and most of those stars have planets. The math seems to do the work for us. Surely, in all of that, something else must have figured out how to breathe, to think, to look up and wonder. It would almost be arrogant to think otherwise, right? That's the comfortable assumption, and it's the one we're going to take apart tonight. Because here's what most people don't realize. The assumption that the universe must be full of life is not a scientific conclusion. It's a feeling. It's an intuition based on the sheer size of the place. And feelings, even well-intentioned ones, have a habit of being wrong when the universe is involved. What we actually know, when we look carefully and honestly at the evidence, is much stranger and much more unsettling than either the optimists or the pessimists tend to admit. By the time we finish tonight, you're not going to walk away with a neat answer. Nobody has one. But you are going to understand the question in a way that most people never get to. You're going to see why the silence from the sky is the single most important scientific mystery of our time. And you're going to understand why one of the most credible answers to that mystery is also the one that should keep us up at night. Let's start at the beginning. Let's start with what we actually know about how common life should be and what the universe has actually shown us so far. The universe is roughly 13.8 billion years old. That number is real and verified and has been measured multiple ways, and it sits in the background of everything we're going to talk about tonight, like the foundation of a building. 13.8 billion years. If you compress that entire timeline into a single calendar year, with the Big Bang happening on January 1st at midnight, the Earth wouldn't form until early September. Dinosaurs would appear on December 25th, and every single thing that humans have ever done, every war, every poem, every city, every scientific discovery, would happen in the last 12 seconds before midnight on December 31st. That's how new we are. But here's the part that matters. For much of that year, the universe was already doing what it needed to do to eventually produce life. Stars were forming and dying. Heavy elements were being forged inside their cores and scattered by supernovae. The raw ingredients for chemistry, for biology, for everything that eventually became you and me, were being assembled for billions of years before the Earth even existed. The Milky Way, the galaxy we live in, is about 100,000 light years across. Just to feel that number, a light year is roughly 5.88 trillion miles. So if you drove the diameter of our galaxy at highway speed without ever stopping, not for gas, not for sleep, just driving constantly, it would take you about 1.1 quadrillion years. That's about 80,000 times the current age of the universe. We live in a place that is, by any standard we can apply, unimaginably large. And the Milky Way contains somewhere between 100 billion and 400 billion stars. Scientists generally use 200 billion as a working number. If you counted one star per second without stopping, it would take you over 6,000 years to count them all, just in our galaxy. And there are at least 2 trillion galaxies in the observable universe. That word, at least, does a lot of heavy lifting. So when someone says surely there must be life out there, you understand why the intuition feels solid. The scale of the thing seems to demand it. If even a tiny fraction of those stars have planets, and if even a tiny fraction of those planets have the right conditions, and if even a tiny fraction of those end up producing life, well, the numbers should still be enormous, right? That's the logic behind the Drake equation, and it's where we need to go next. In 1961, a radio astronomer named Frank Drake sat down with a small group of scientists at a conference in Green Bank, West Virginia. The conference was about the search for extraterrestrial intelligence, a field so new at the time that it barely had a name. Drake wasn't trying to solve the problem that day. He was trying to organize it. He wanted to lay out in a systematic way all the different factors that would go into estimating how many communicating civilizations might exist in our galaxy right now. So he wrote an equation. It wasn't meant to be solved immediately. It was meant to be a framework, a way of listing everything we'd need to know and being honest about everything we didn't. The equation multiplies a series of factors together: the rate of star formation in the galaxy, the fraction of those stars that have planets, the number of those planets that might be capable of supporting life, the fraction that actually develop life, the fraction of those that develop intelligent life, the fraction of intelligent civilizations that develop detectable technology, and how long those civilizations typically survive and keep transmitting signals. Multiply all those numbers together and you get n, the estimated number of active communicating civilizations in our galaxy at any given moment. Drake's original estimate, using the best guesses available in 1961, came out to somewhere around 10 civilizations. 10. In a galaxy of 200 billion stars. That's a number that deserves a moment, not thousands, not millions. 10. And that was the optimistic version. In the decades since, as we've learnt more about each of those factors, scientists have updated the equation with better data. Some of those updates have been encouraging. We now know that most stars have planets. Astronomers have confirmed that. The fraction of stars with planetary systems is close to 1, meaning almost every star you can see has at least one planet orbiting it. That's genuinely good news for the equation. We also know that many of those planets sit in what astronomers call the habitable zone. That's the range of distances from a star where liquid water could theoretically exist on a planet's surface. Not too hot, not too cold, and we found lots of them. The Kepler Space Telescope, which spent 9 years staring at a small patch of sky and monitoring the brightness of stars, found evidence of thousands of exoplanets. Scientists estimate that in the Milky Way alone, there could be as many as 40 billion Earth-sized planets sitting in the habitable zones of their stars. 40 billion potentially habitable worlds just in our galaxy. That's the point where most people's optimism kicks in fully. 40 billion chances. Surely something good happens somewhere. But here's where the equation starts to get uncomfortable. The factor that makes the Drake equation tricky isn't the number of stars or planets. Those we can measure, or at least estimate with confidence. The factor that makes everything fall apart is the one that asks, of all the planets that could support life, what fraction actually develop it? We call that factor FL, the fraction of habitable planets where life actually arises. And we have absolutely no idea what that number is. We have exactly one data point, Earth. And one data point isn't a sample, it's just a story. We can't look at a single coin flip and conclude that coins always land heads. We can't look at Earth and conclude that life always emerges on habitable planets. We genuinely do not know if the origin of life is something that happens easily, almost automatically given the right conditions, or something that requires such a specific and unlikely sequence of events that it might only have happened once in the entire history of the universe. And that uncertainty, that single unknown, changes everything else in the equation. If life emerges easily on every habitable planet, the Milky Way might be crawling with civilizations. If life requires a miracle, we might be it. Let's talk about what life actually requires. Not in the abstract, but specifically. Because the more we look at the origin of life on Earth, the more we realize we don't actually understand how it happened. And that's a problem. We know that the Earth is about 4.5 billion years old. We know that the first evidence of life, simple single-celled organisms, appears in the fossil record at about 3.7 billion years ago, possibly earlier. That means life appeared on Earth within the first 800 million years of the planet's existence, possibly faster. 800 million years sounds like a long time, but in geological terms, it's fairly quick. The fact that life appeared so rapidly after the Earth cooled down is often cited as evidence that life might emerge easily, given the right conditions. But there's a counter-argument to that, and it's one you don't hear as often. The counter-argument is something called observational selection bias, and it goes like this. If life hadn't emerged quickly on Earth, we wouldn't be here to notice. Only a planet where life arose quickly could produce beings capable of looking back and measuring how quickly life arose. So the fact that we observe life emerging quickly on Earth tells us almost nothing about how likely that process is in general. We're only capable of making this observation because we're here, and we're only here because it worked. That might sound like a logic trick, but it's actually a serious methodological concern. It means we can't use Earth's early life as strong evidence that life is common. We'd see the same pattern whether life is common or whether it's astronomically rare. Either way, we would always find ourselves on a planet where it happened quickly, because those are the only planets that produce observers. So where does that leave us? It leaves us needing other evidence. We need to find life somewhere else. Even single-celled microbial life, on Mars, on one of Jupiter's moons, somewhere in our own solar system, would be transformative. It would tell us that life didn't just happen once, it happened twice, or more, in the same small neighborhood. And if it happened twice in our cosmic backyard, the implication would be that it's happening everywhere, constantly, that the universe is teeming with it. But if we search Mars thoroughly, if we explore the subsurface oceans of Europa and Enceladus and Titan, and we find nothing, that changes the picture dramatically. Not finding life in our own solar system wouldn't prove life is rare, but it would be a meaningful data point. And right now, after decades of Mars missions and careful searching, we haven't found it. The silence within our own solar system is its own quiet kind of data. Now let's talk about the Fermi paradox, because this is where the story gets really strange. In the summer of 1950, a physicist named Enrico Fermi was walking to lunch with some colleagues at Los Alamos National Laboratory in New Mexico. They'd been talking casually about a recent news story about flying saucers, and Fermi had been making jokes about it. But sometime during lunch, apparently out of nowhere, he put down his fork and asked a question that nobody in the room could quite shake. He said, "Where is everybody?" That's it. That was the question, and it's one of the most profound questions in all of science. Here's the setup. If the universe is as old as we know it is, 13.8 billion years, and if intelligent life is even moderately common, then civilizations should have had billions of years to develop and spread. Even if interstellar travel is hard, even if it takes thousands of years to cross the distances between stars, a civilization that gets a head start of even a few million years on us should have been able to colonize the entire galaxy by now. The Milky Way is 100,000 light years across, but even at a tiny fraction of the speed of light, a civilization with enough time and motivation could have filled it completely. The physics allows it, the time frames allow it, and yet we see nothing. We hear nothing. There are no signals, no artifacts, no visitors, no evidence of any kind that anyone else has ever been here or is out there. Fermi's question wasn't really about flying saucers. It was about the math. The math says someone should have been here by now. The sky says no one is. That gap between what the math predicts and what we actually observe is called the Fermi paradox. And in the 70-something years since Fermi asked his lunch table question, nobody has satisfactorily answered it. Let's think about what kind of gap we're talking about, because the numbers make it even stranger. Our Sun is about 4.6 billion years old. That makes it a relatively young star in galactic terms. There are stars in the Milky Way that are 10 or even 12 billion years old. Those stars could have had Earth-like planets forming around them 8 billion years ago. That's 3.4 billion years before our planet even existed. If life arose on one of those planets as quickly as it did on Earth, that civilization has had a 3.4 billion year head start on us. To put that head start in scale, the distance between where we are technologically today and where we were 3.4 billion years ago is the distance between modern surgery and a bacterium. The gap is incomprehensible. A civilization with a 3 billion year head start would be, relative to us, what we are to a rock, not even a worm, a rock. And yet that civilization, if it exists, has left no trace we can find, no signals, no megastructures, no evidence of resource use on a galactic scale. Nothing. That's the paradox. Not just the silence, but the specific kind of silence that seems to require explanation. There are dozens of proposed solutions to the Fermi paradox. Scientists and philosophers have been working through them seriously for decades, and we're going to walk through the most important ones tonight, because each one teaches us something different about either the universe or ourselves. Let's start with the ones that keep life alive, the solutions that say intelligence is common but undetectable, before we get to the darker ones. The first and most popular comfortable solution is what's sometimes called the zoo hypothesis. The idea was formally proposed by astronomer John Ball in 1973, though versions of it had been floating around science fiction for decades before that. The zoo hypothesis says that intelligent civilizations do exist, possibly many of them, but they've chosen not to contact us, either out of respect for our development, the way we might observe a nature reserve without disturbing it, or for reasons we can't imagine. They're simply watching, keeping their distance, waiting for something. It's a calming idea. It implies we're not alone. It implies we're monitored, perhaps even cared for, like a protected species. There's something almost comforting about it. But the hypothesis has a serious problem. It requires perfect coordination among every single technological civilization in the galaxy for millions of years, without exception. Every civilization that has ever developed the ability to communicate across interstellar distances would need to have independently arrived at the same decision: don't contact the humans. And none of them could break ranks, not one, because if even a single civilization out of thousands or millions decided to make contact or accidentally leaked a signal or sent a probe just to see what would happen, we'd know about it. One defection ends the hypothesis. The statistical improbability of that kind of perfect, sustained, universal agreement is itself a significant problem. Human civilization can't maintain universal consensus on anything for a century, let alone for millions of years across thousands of independent species who've never even met. So while the zoo hypothesis is emotionally satisfying, it's structurally weak. It requires more coordination and more deliberate silence than almost any other explanation. The next explanation is what's called the dark forest theory, and it's the opposite of comforting. The name comes from a science fiction novel by Chinese author Liu Cixin, but the underlying logic is serious enough that scientists and philosophers discuss it as a genuine possibility. The dark forest theory says that the universe is quiet not because civilizations are absent, but because every civilization that reaches a certain level of sophistication quickly realizes the same terrible truth: revealing your existence is dangerous, possibly fatal. So everyone goes silent. Here's the logic. The universe is enormous, and the resources within it, energy, matter, habitable planets, are finite. Any sufficiently advanced civilization knows this. It also knows something else. it cannot verify the intentions of any other civilization it might contact. You can receive a signal from across the galaxy, you can even decode it, but you can never be certain, not completely, that the civilization sending it is friendly, and the cost of being wrong is extinction. So the rational move, if you're a civilization that's been around long enough to think carefully about this, might be to stay silent and to eliminate any civilization you become aware of before it becomes a threat to you. Not out of malice, out of pure strategic logic, the same way a person hiking alone at night in genuinely dangerous territory might not want to call out to announce their presence. In this model, the galaxy is like a dark forest full of hunters. Everyone knows the others are out there, everyone is hiding, and anyone who makes a sound risks getting found. This theory is viscerally unsettling, and there's a version of it that's even harder to shake. The version that says that if the dark forest is real, then our own radio transmissions, which have been leaking into space since the early 20th century, have already done the thing we shouldn't have done. We've made a sound in the forest. Our radio and television signals have been spreading outward from Earth at the speed of light for about 120 years. That means a sphere of radio noise with Earth at its center has expanded about 120 light-years in every direction. There are roughly 15,000 star systems within that sphere. Any civilization within that sphere with the right equipment could in principle have detected us. Whether the dark forest model is right or wrong, this is a real and measurable fact. The universe has known about us, or at least had the opportunity to know about us, for over a century now. We opened the door a long time ago. But most physicists and astronomers are skeptical of the dark forest theory for practical reasons. The distances involved are so enormous that even detecting another civilization's signals would require technology we don't have and possibly can't build, and actually reaching another civilization to threaten them within any time frame that matters to any individual civilization might simply be impossible. The galaxy is not a dark forest where hunters can move quickly. It's more like a dark ocean, where the nearest other boat is decades or centuries away at best. So the dark forest theory is a real hypothesis, but it's not the strongest one. Let's talk about one that's more empirical, one that's grounded in biology and chemistry rather than game theory. It's called the rare earth hypothesis, and it was laid out systematically by paleontologist Peter Ward and astronomer Joe Kirschvink in a book published in 2000. The argument is straightforward and worth sitting with. The rare earth hypothesis says that the emergence of complex multicellular life, the kind that can eventually produce intelligence, requires such a specific and unlikely combination of factors that it may have happened only once, or at least extremely rarely. It's not that life can't emerge. Simple microbial life might be common, but the jump from simple life to complex life, to animals, to brains, to technology, requires a list of conditions so long and so specific that Earth may be genuinely unusual. Let's go through some of those conditions because they're worth understanding. First, Earth is in the right part of the galaxy. The Milky Way has a structure, and not all parts of it are equally hospitable to life. The galactic center is dense, crowded with stars, and bathed in intense radiation from the supermassive black hole at its core. The outer edges of the galaxy are too sparse, with too little of the heavy elements needed for rocky planets and complex chemistry. Earth sits in what's sometimes called the galactic habitable zone, a broad ring at the right distance from the center where conditions are relatively calm, heavy elements are abundant, and catastrophic radiation events are less frequent. Second, our Sun is an unusually stable and unusually calm star. Most stars in the Milky Way are M-dwarf stars, which are smaller and cooler than our Sun. They're by far the most common type of star, making up about 75% of all stars, and they have planets, lots of them. Many of those planets orbit within the habitable zone of their star. But M-dwarf stars have a problem. They're violently active, especially when young. They flare constantly, blasting out radiation and charged particles that would strip away the atmospheres of any nearby planets. A planet sitting in the habitable zone of an M-dwarf is essentially orbiting a small, unpredictable bomb that goes off regularly for billions of years. Our Sun is a G-type star, relatively calm, relatively stable, relatively well-behaved. It still has flares, it still has storms, but compared to most stars, it's a gentle neighbour. That might matter more than we've historically given it credit for. Third, Earth has a massive moon. Our moon is unusually large relative to Earth's size. No other rocky planet in our solar system has anything like it. The moon stabilizes Earth's axial tilt. Without the moon's gravitational steadying influence, Earth's axial tilt would wobble chaotically over millions of years, swinging from nearly 0 degrees to as high as 85 degrees. That would produce climate swings so severe, so fast, and so extreme that complex life might never have had the stable, consistent conditions it needed to develop and survive over hundreds of millions of years. The moon's presence might be one of the unsung reasons that life on Earth made it from microbes to mammals. How did we get such an enormous moon? Almost certainly by a collision. About 4.5 billion years ago, a Mars-sized body called Theia smashed into the early Earth at an angle. The debris from that impact coalesced into our moon. It was a chance event, a specific, unrepeatable kind of cosmic accident. There's no reason to think that most habitable planets get hit in exactly the right way, at exactly the right time, to produce a moon of the right size. Fourth, Jupiter. The largest planet in our solar system sits at just the right distance from the Sun and has just enough mass to act as a gravitational shield for the inner solar system. When long-period comets come crashing inward from the outer solar system, Jupiter's gravity either deflects them or captures them. Without Jupiter doing that job, the inner planets, including Earth, would be bombarded far more often and far more violently by impactors. The frequency and severity of mass extinction events might be so high that complex life never gets enough time to develop and stabilize before the next catastrophe wipes the slate clean again. Not every solar system has a Jupiter, and even in systems that do have a large outer planet, it's not always in the right place or the right size to perform this protective function. In many of the planetary systems we've discovered around other stars, the large gas giants are actually in the inner part of the system, close to the star, in a configuration that would make life on inner rocky planets almost impossible. Fifth, plate tectonics. Earth's crust is broken into plates that drift and collide and sink and rise, driven by heat from the planet's interior. This process, which we call plate tectonics, does several things that are critically important for complex life. It recycles carbon dioxide back into the atmosphere through volcanic activity, helping to regulate Earth's temperature over long periods. It builds mountains, which create diverse climates and ecosystems. It drives the mixing of minerals and nutrients through the ocean, and it appears to be connected to the generation of Earth's magnetic field, which protects us from the solar wind's most damaging effects. Not every rocky planet has plate tectonics. Mars almost certainly doesn't, or at least not active plate tectonics today. Venus doesn't appear to have it in the way Earth does. The conditions required for plate tectonics, just the right amount of interior heat, just the right composition of the crust, just the right amount of water in the rocks, seem to be fairly specific. And without it, a planet's temperature regulation breaks down, its carbon cycle stalls, and the sustained habitability that complex life requires might never materialize. Put all of this together, and the picture becomes clear. Earth isn't just a rocky planet in a habitable zone. Earth is a planet that got lucky in a long list of ways, some of which we understand, many of which we're still figuring out. And each additional requirement, each additional and also, shrinks the probability of a planet producing complex life. The rare Earth hypothesis doesn't say life is impossible elsewhere. It says the bar is higher than most people assume. Microbial life might be everywhere, but the kind of life that picks up a radio telescope and points it at the stars that might be genuinely rare. Which brings us to what some scientists think is the real answer to the Fermi paradox. The answer that is in certain ways the most unsettling of all. It's called the Great Filter. The Great Filter is a concept introduced by economist Robin Hanson in 1998. The logic is clean and hard to dismiss. We know that the universe is old. We know it contains an enormous number of stars and planets. We know that in principle, the conditions for life and intelligence are not unique to Earth. And we know that given enough time, a civilization that reaches our level of technology could theoretically spread across the galaxy. We also know, with a confidence that grows every year we keep listening, that nobody has done that. No one has colonized the galaxy. No one is broadcasting in a way we can detect. Nobody has built megastructures around stars that we can observe. The galaxy is quiet. For the galaxy to be quiet, something must be preventing civilizations from expanding across it. Something is filtering them out. That something is the Great Filter. The Great Filter is some step in the process from basic chemistry to galaxy-spanning civilization that almost nothing gets through. Some challenge or transition or event that is so difficult, so unlikely, or so catastrophic that it eliminates virtually all candidates before they can reach the next level. Something is stopping civilizations from making it to the end. The question that makes the Great Filter so important and so personally relevant to us is this: is the Great Filter behind us, or is it ahead of us? If the Great Filter is behind us, we've already passed it. It was some step in our past that was improbably difficult. Maybe it was the origin of life itself, the first self-replicating molecule emerging from a prebiotic soup of chemicals might be so improbable that it's happened only once in 13.8 billion years of cosmic history. Or maybe it was the development of the eukaryotic cell, the complex type of cell with a nucleus that all plants, animals, and fungi are made of. That transition happened only once in the history of life on Earth, about 2 billion years ago, and took 1.5 billion years after life first appeared to accomplish. Maybe that particular evolutionary innovation is the rare step that most living worlds never managed to take. If the Great Filter is behind us, we are astonishingly lucky. We survived the hard part. The universe may be full of dead worlds covered in microbial slime, but we're the fluke that made it through. And in that case, the silence of the universe makes sense. We're not necessarily alone forever. We may just be extraordinarily early, the first civilization to reach our level in this galaxy, with millions of years of potential history still ahead of us. That would be good news. Strange, lonely news, but good news. But if the Great Filter is ahead of us, then the quiet universe is telling us something much darker. It means that some step between where we are right now and where we imagine we're going is so lethal that almost no civilization survives it. Something is killing them. Something consistently, reliably, and completely eliminates technological civilizations before they can expand and make themselves known. And we don't know what it is. Maybe it's nuclear war. Maybe every civilization that develops nuclear weapons eventually uses them. Maybe the same cognitive evolution that produces curiosity and problem solving also produces tribalism and aggression, and at a certain level of technological power, tribalism and aggression win. Maybe it's artificial intelligence. Maybe every civilization that develops artificial general intelligence eventually creates something that supersedes them and either eliminates them or redirects the civilization in a way that makes it go quiet, becoming something we wouldn't recognize as a broadcasting, expanding civilization. Maybe it's resource depletion. Maybe every industrial civilization runs through its planet's resources before it can establish itself beyond its home world, and the window for escape is narrower than anyone anticipates. Maybe it's something we haven't thought of, a physical law we don't know about, a chemical process that poisons civilizations at a certain scale, a cosmic event like gamma-ray bursts that periodically sterilizes regions of the galaxy. The uncomfortable truth is that we have no way to know which of these it is, or even which category the Great Filter falls into, until we find out the hard way. Now here's where the search for extraterrestrial life stops being just an interesting scientific question and becomes something deeply personal. When we search for life elsewhere in the universe, one of the most important things we can find is complex life. Multicellular organisms, animals, things with brains. The more complex and evolved the life we find, the more we can infer about where the Great Filter sits. And the more we find, the more worried we should be. Think about it this way: if we explore Mars in detail and find nothing at all, not even microbial life, not even the chemical signatures of ancient biology, then the Great Filter probably sits early, at or before the origin of life. That's actually okay for us. It means we're past the filter. We're one of the rare worlds where life happened. If we find microbial life on Mars, or in the oceans of Europa, or in the hydrocarbon lakes of Titan, that changes the picture. It means simple life is common. It means the Great Filter probably doesn't sit at the origin of life, which means it sits somewhere else, somewhere later. That narrows the possibilities and moves the filter closer to us. If we find the ruins of a dead civilization somewhere in the solar system, or if we receive a signal from a civilization that has since gone silent, or if we see evidence of a technology that was advancing but stopped, the implications would be profound and disturbing, because it would suggest that civilizations do arise, they do reach technological capability, and then something happens. Something ends them, something that hasn't happened to us yet. The astronomer and SETI researcher Seth Shostak puts it this way: finding simple life elsewhere would be encouraging, but not settle the question. Finding complex life elsewhere would be exciting, but start raising alarms. Finding the ruins of a dead civilization would be the most terrifying discovery in human history. Not because of monsters, because of what it would imply about us. This is why some scientists have argued, seriously and with genuine concern, that we should be very careful what we wish for when it comes to the search for extraterrestrial life. The thing we most want to find, evidence that we're not alone, might simultaneously be the thing that tells us we're running out of time. Let's go back to the Drake equation for a moment, because there's one factor we haven't talked about yet, and it's arguably the most important one. It's the last factor in the equation. Scientists call it L, the average lifespan of a technological civilization. Drake's equation works by multiplying all those factors together to get a number, but if you multiply any number by 0, you get 0. And if you multiply by a very small number, you get a very small number. L is the factor that most heavily determines the final answer, because it represents how long a civilization like ours actually survives once it develops the ability to communicate across interstellar distances. If technological civilizations typically last only a few hundred years before destroying themselves or going quiet, then the number of active civilizations in the galaxy at any given moment is very small. Even if new ones keep arising, at any given snapshot in time there might only be a handful of them, spread across 100,000 light-years of space, with no way of finding each other. Ships passing in the night on a very, very large ocean. But if technological civilizations typically last millions or billions of years, then even if the conditions for their formation are rare, there should be many of them coexisting at any given time. The silence of the sky becomes much harder to explain. The challenge is that we have exactly one example of a technological civilization, and it's only been technologically advanced for a few hundred years. We have no idea what a 10,000-year-old technological civilization looks like, let alone a million-year-old one. We can speculate, we can model, but we don't know. And we don't know if we're going to make it. The honest acknowledgement that we might be within the window of our own great filter, whatever it is not comfortable, but it's honest. Human civilization has been technologically capable of self-destruction for about 80 years. That's the time since the first nuclear weapons were tested. In terms of our planet's total lifespan of 4.5 billion years, 80 years is such a small fraction that it doesn't even register on a geological timescale. If you plotted Earth's entire history on a 100-meter track and field lane, the nuclear era would occupy a distance thinner than a pencil line near the finish. We have, in other words, been dangerous to ourselves for an amount of time so brief it barely counts. And in that tiny sliver of time, we came very close to using those weapons on multiple occasions. The Cuban Missile Crisis in 1962 is the most famous near miss. Two superpowers, both armed with hundreds of nuclear warheads, each one many times more powerful than the weapon that destroyed Hiroshima, came within hours of an exchange that some analysts believed could have killed hundreds of millions of people and triggered a nuclear winter lasting years. There were others. In 1983, a Soviet lieutenant colonel named Stanislav Petrov was on duty when his monitoring systems reported an incoming American missile launch. Protocol required him to report it up the chain of command, which would have triggered a Soviet counter-launch. He decided, on his own judgment, that it was probably a false alarm. He was right. A satellite had mistaken sunlight reflected off clouds for a missile launch. His decision not to follow protocol may have prevented a nuclear exchange that would have altered the course of human history. There was a Soviet submarine during the same crisis in 1962, the B-59, that came under depth charge attack from American forces and lost communication with Moscow. The submarine's commander believed war had broken out. To launch their nuclear torpedo, they needed agreement from 3 officers. The captain and the political officer both agreed to launch. The second in command, a man named Vasily Arkhipov, refused. He argued they should surface first and try to make contact. He was right, and his decision may have prevented the escalation that would have followed a nuclear strike against American ships. 2 moments, 2 individual human beings, and the entire history of what followed. Every person born since 1963, every scientific discovery, every work of art, every moment of ordinary human life across 60+ years may have balanced on the choices of those individuals. If that's the kind of knife's edge that all technological civilizations navigate, is it surprising that the galaxy seems empty? Now let's talk about something that takes the Fermi paradox in a different direction entirely. Something that shifts the question from where are they to why aren't they here already? This is the idea of interstellar colonization, and the math behind it is worth understanding. When scientists think about a civilization expanding through the galaxy, they don't have to assume faster than light travel or any exotic physics. They just need to assume that a civilization can build ships capable of traveling at, say, 1% of the speed of light. That's fast by human standards. But at 1% of the speed of light, the nearest star system to ours, Alpha Centauri, at about 4.2 light-years away, would take 420 years to reach. That's a long journey, but not an impossible one to organize for a civilization with a long-term perspective. Once a colony is established at Alpha Centauri, it can build its own ships and send colonists to the next nearest systems, and those colonies can do the same. A colonization wave expanding at 1% of the speed of light, even accounting for the time needed to settle and establish each new colony before sending out the next wave, could theoretically reach every star in the Milky Way in somewhere between 5 and 50 million years. 50 million years sounds like a long time, but we said earlier that some stars in the Milky Way are up to 12 billion years old. A civilization that arose 5 billion years ago, even one that only managed to colonize the galaxy at 1% of the speed of light, should have finished doing so roughly 4.95 billion years ago. The galaxy should be fully settled. Every habitable planet should bear the marks of some ancient civilization's visit, if not their active presence. It doesn't, as far as we can tell. Some scientists point out that maybe we haven't looked hard enough. The galaxy is enormous, But astronomers have done extensive surveys looking for the signatures of large-scale technological activity, things like waste heat from megastructures, unusual patterns of star consumption, signs of stellar engineering. The Fermi paradox isn't just about the absence of radio signals, it's about the absence of any anomalous signatures at all, in the stars, in the galaxies we observe, in the deep sky surveys conducted by observatories around the world. Nothing is obviously unmistakably artificial on a galactic scale. Now, some researchers argue that absence of evidence isn't evidence of absence. We could be missing signs that are obvious to a more sophisticated observer. Our instruments are limited. Our understanding of what an ancient technological civilization would look like may be completely wrong. Maybe they've evolved beyond any technology we can recognize. That argument is reasonable, but it has a limit. There are things that would be hard to miss. A Dyson sphere, a structure built around a star to capture most of its energy output, would dramatically alter the star's observed spectrum and infrared signature in ways our telescopes can detect. We've searched specifically for stars with those signatures. A project called Glimpsing Heat from Alien Technologies, or GHAT, surveyed about 100,000 nearby galaxies looking for unusually high infrared emissions that might indicate a galaxy-spanning civilization harvesting the energy output of billions of stars. They found nothing that couldn't be explained by natural processes. A galaxy that contains billions of years of civilizational development should look different from a sterile one. We've been watching closely, and it looks sterile. Let's slow down and sit with the possibility that it's actually true, that we really are alone. Not alone in the sense of no microbes on other planets, but alone in the meaningful sense, alone as the only civilization, the only things in this galaxy that have ever developed language, or built a telescope, or wondered about their own existence. What would that actually mean? It would mean that in a galaxy of perhaps 400 billion stars, orbiting trillions of planets, over a history of 13.8 billion years, the universe managed exactly one experiment in complexity and consciousness, us, on this small, damp, slightly lopsided planet orbiting an unremarkable yellow star in one of the galaxy's quieter spiral arms. It would mean that every story ever told, every piece of music ever composed, every philosophical argument ever made, every moment of ordinary human experience, like waking up on a quiet morning with coffee and the sound of birds outside the window, is a singular event in cosmic history. There is no duplicate, no echo, no parallel. These things happened here and only here, and so far they have happened nowhere else. That's not a comfortable thought, but it's also not a small one. There's a version of cosmic loneliness that is at the same time cosmic significance. If we are the only witnesses to the universe's own existence, then we are not trivial. We are, in some sense, what the universe uses to look at itself. Carl Sagan said something along these lines. He said, "We are a way for the cosmos to know itself." That line is famous enough to have become a cliché, but the underlying idea deserves more than a bumper sticker. If no other intelligence exists in our galaxy, then we are literally the only perspective that this entire galaxy has ever had on its own existence. Every neutron star, every black hole merger, every supernova going off in the night sky has unfolded in total darkness, unwitnessed, unmourned, until we came along and pointed our instruments at it and said, "That happened 60,000 years ago, and here's what it looked like." We gave the galaxy a memory. We gave the universe a mirror. And if we don't survive, if we become another entry in the growing list of great filter candidates, that mirror goes dark. Not just for us, for everything. Now let's talk about something that we've been dancing around, something that's specifically relevant to the era we're living in. Because the Great Filter isn't just a historical concept, it's also a forward-looking one, and some scientists believe we may be entering the zone of the filter right now. The 21st century is unlike any previous century in human history, not because of its scale, or its population, or its technology alone, but because of the specific combination of capabilities we've developed and the specific vulnerabilities they've created. We can now edit the genome of living organisms with precision. We can design microorganisms. We can build autonomous systems capable of learning and improving themselves. We can release chemicals into the atmosphere that change the global climate in ways that will persist for centuries. We can store enough destructive power in enough hands that a single decision by a single actor could reshape the world permanently. All of these things arrived within roughly the same human lifetime. They came so fast, and we built the systems to manage them so slowly, that the gap between capability and governance has never been wider. We are, as a civilization, extremely capable and not particularly wise about those capabilities. That's not a moral judgment, it's just an observation. Some researchers, including Oxford philosopher Nick Bostrom, have argued that the development of artificial general intelligence, a machine intelligence that can improve itself beyond human capabilities, might represent a particularly dangerous transition point, not because of science fiction scenarios involving evil robots, but because of something more subtle. The challenge of ensuring that a system vastly more capable than its creators remains aligned with human interests and values is genuinely unsolved. It's not clear that it can be solved, or that we'll solve it in time. Bostrom's argument is that many of the catastrophic risks facing civilization this century have a specific property: they're irreversible. A nuclear exchange that kills 1 billion people is catastrophic, but humanity survives and rebuilds. A pandemic that kills half the population is devastating, but life continues. But some risks aren't like that. Some risks have terminal outcomes, and the more capable our technology becomes, the more terminal risks enter the picture. Whether or not you find that analysis persuasive, it's worth noticing that the pattern it describes, civilizations arising, developing powerful technologies, and then facing risks that scale with those technologies, is exactly the pattern the Fermi paradox seems to predict if the Great Filter lies ahead of us. Let's take a step back and think about what we've covered so far, because we've been moving through a lot of ground, and it's worth seeing it whole. We started with the size of the universe, a cosmos containing at least 2 trillion galaxies, each with hundreds of billions of stars, most of them with planets, many of those planets in zones where liquid water is possible. We noted that by pure numbers, the universe seems to demand the existence of other intelligent life. We introduced the Drake equation, the systematic attempt to estimate how many communicating civilizations might exist in our galaxy, and noted that it works well for the factors we can measure and completely breaks down at the factors we can't. Specifically, we have no idea how often simple life gives rise to complex life, and no idea how long civilizations typically survive once they become technological. We walked through the rare Earth hypothesis and the long list of specific conditions that may have been required for Earth to produce complex life. The galactic habitable zone, the stable sun, the large moon, the protective Jupiter, the plate tectonics, each one a requirement that narrows the probability. We sat with the Fermi paradox itself, the strange and persistent silence of a universe that by the numbers should be full of noise. The absence not just of signals, but of any detectable large-scale engineering, any colonization wave, any evidence that intelligence has existed and expanded anywhere in our observable neighborhood. We walked through the proposed solutions, the zoo hypothesis, the dark forest, the Great Filter, and considered each one's strengths and weaknesses. And we arrived at the Great Filter as the framework that most honestly engages with the silence, while raising the most uncomfortable question: is it behind us or ahead of us? Now let's go deeper into some of the specific scientific evidence that bears on that question, because there are data points we haven't talked about yet that are genuinely strange and genuinely relevant. Let's talk about the origin of life, not in general terms, but specifically, because the more scientists study it, the stranger it gets. Life, as we know it, requires three things working together. A way to store information, which DNA does through its sequence of base pairs, a way to copy and express that information, which proteins do, and a membrane to contain and separate the chemistry from its environment. The problem is that each of these three things depends on the other two. DNA needs proteins to be copied. Proteins are made using instructions from DNA, and the membrane that protects both of them is made using proteins. None of these things can exist, functionally, without the other two. How did the first living cell get all three of these systems working simultaneously, from scratch, in a prebiotic soup of random chemicals? Scientists have been working on this question for over half a century, and they don't have a complete answer. The most popular current hypothesis involves RNA, a molecule that can both store information like DNA and perform chemical functions like proteins. Maybe RNA came first and was the original information and function molecule before DNA took over the information storage role and specialized proteins took over the catalytic role. This is called the RNA world hypothesis. There's evidence for it. There are RNA molecules called ribozymes that catalyze chemical reactions. RNA can fold into complex three-dimensional shapes that let it do chemistry, and RNA can self-replicate under certain conditions in the lab, which is the key property any first molecule of life would need. But the RNA world hypothesis has unsolved problems too. The chemical conditions required to produce RNA molecules from simpler precursors are quite specific and not obviously present in any particular early Earth environment. And the spontaneous self-assembly of the first RNA molecule capable of self-replication would have required a remarkable set of coincidences. Not impossible, but not easy. There's another approach that focuses less on the molecule and more on the chemistry. Some researchers, including the origin of life chemist Michael Russell and the geologist William Martin, have argued that life didn't begin in a warm little pond as Darwin famously speculated. It began at hydrothermal vents at the bottom of the ocean, specifically the alkaline kind, where a natural chemical gradient between the vent fluid and the ocean water could have driven the first energy-producing reactions without needing any complex molecules at all. This is an active, live debate in science. Nobody has cracked it, and the fact that we have been studying the origin of life seriously for over 70 years and still can't reproduce it in the lab, not fully, not definitively, tells us something. Either it's genuinely hard to do, or we're missing something fundamental about how it works. If it's genuinely hard to do, that's a vote for the great filter being at the origin of life. If we're missing something simple, some physical or chemical process that makes it trivially easy given the right conditions, then the filter isn't there and we need to look elsewhere. We genuinely don't know, and that uncertainty is real and active and ongoing, not a thing that was solved and put away. Now let's talk about the Cambrian explosion, because this is one of the most important and least discussed events in Earth's history when it comes to the Fermi paradox. For the first roughly 3 billion years of life on Earth, life was essentially all microbial. Single-celled organisms, simple colonies, nothing with tissues or organs or anything we'd recognize as an animal body plan. Bacteria ruled the Earth, and then, about 541 million years ago, something happened. In a geological blink, maybe 10 to 25 million years out of 4.5 billion, something that's essentially instantaneous on geological timescales, nearly all the major animal body plans we know today appeared in the fossil record. Eyes, limbs, shells, bilateral symmetry, predation, complex nervous systems, the full zoo of animal architectures that has diversified and evolved ever since, showed up all at once in what paleontologists call the Cambrian explosion. Why did it happen? We don't fully know. The development of eyes may have been a key trigger, creating a sudden evolutionary arms race between predators and prey. Changes in ocean chemistry may have made it possible to build mineralized shells. A rise in atmospheric oxygen may have made complex metabolism possible. The end of a global glaciation event, a period sometimes called Snowball Earth, may have opened new ecological niches. All of these have been proposed. Probably more than one was involved. But here's what's relevant to our conversation. The Cambrian explosion happened once, in 4.5 billion years of Earth history, with life present for at least 3.7 billion of those years. The explosion of complex multicellular animal life happened exactly one time, just once. It wasn't a repeating process. It wasn't something that kept reoccurring. It was a singular event, triggered by a convergence of conditions that took billions of years to arrange themselves. If that kind of convergence is rare, not just on Earth but everywhere, then complex animal life, and by extension intelligent life, might be rare everywhere too. Another vote for the early Great Filter. Let's also consider the emergence of the eukaryotic cell, because this is another transition that might be even harder than the origin of life. All life on Earth falls into two categories: prokaryotes, which are simple cells without a nucleus, including all bacteria and archaea, and eukaryotes, which are more complex cells with a membrane-bound nucleus, including all plants, animals, fungi, and most of the other complex organisms we know. Every multicellular organism, every animal, every tree, every mushroom is made of eukaryotic cells, and the eukaryotic cell appears to have originated exactly once in Earth's history, roughly 2 billion years ago, through an event called endosymbiosis. In this event, one cell engulfed another, and instead of digesting it, incorporated it as an organelle. The mitochondria, the energy-producing structure found in almost every eukaryotic cell, is actually a bacterial cell that was incorporated into a host cell approximately 2 billion years ago and never left. This happened once. In 3.7 billion years of microbial life, this particular merger happened one time, and it gave rise to all complex life. If it hadn't happened, if that one bacterium in that one archaea, in that one ancient ocean hadn't been engulfed in just the right way, Earth today might still be a world covered in simple microbial mats, with nothing more complex than a biofilm. And we'd never know. We wouldn't be here to know. The endosymbiosis event is another candidate for the Great Filter. Another step that looks in retrospect like an improbable turning point that almost didn't happen. Every time scientists look carefully at the history of life on Earth, they find these narrow gates, these moments where the story could easily have branched differently, toward a simpler, quieter, and ultimately dead-end world. Now, I want to talk about something that's come up more seriously in scientific circles in recent years. The idea that we might need to be more careful about what it actually means to search for life. For most of the history of SETI, the search for extraterrestrial intelligence, the approach has been to look for radio signals. The reasoning was simple. If a civilization somewhere is broadcasting, they'll probably use radio waves, because radio waves travel efficiently through space and are a natural product of technological development. So we listen. We've been listening systematically since 1960, when Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for 200 hours. We've been listening in one form or another ever since. And we've heard exactly one thing that made people genuinely excited. In 1977, astronomer Jerry Amon was reviewing data from the Big Ear Radio Observatory at Ohio State University. He was looking through computer printouts of signal data when he saw something that stood out so dramatically from the background noise that he circled it in red ink and wrote "WOW" in the margin. The signal, now known as the WOW signal, lasted 72 seconds, had all the characteristics that SETI researchers had said they'd expect from an artificial signal from deep space, and was never heard again. In the decades since, astronomers have pointed instruments at that same patch of sky many times, looking for a repeat. It hasn't repeated. What caused it remains unknown. Most researchers consider natural explanations more likely than artificial ones. but it hasn't been definitively explained. It remains an open file. Since the WOW signal, more powerful instruments, better data processing, and wider sky coverage have not turned up anything comparable. The SETI effort has grown substantially. The Breakthrough Listen initiative, funded by Russian billionaire Yuri Milner to the tune of $100 million, has been running since 2015 and is by far the most comprehensive SETI program ever undertaken. It's used some of the world's largest radio telescopes to survey the million nearest stars to Earth and the 100 nearest galaxies in multiple frequency bands with unprecedented sensitivity. As of the time we're talking, it hasn't found anything that can't be explained by human-made radio frequency interference or natural astrophysical processes. That's a long time of careful, sophisticated listening, and the silence continues. But here's something worth considering. The search so far has covered almost nothing. Even the most comprehensive surveys have examined a tiny, tiny fraction of the possible signals, frequencies, directions, and types of detectable technology that could exist. To put it in scale, imagine the search for alien signals as a search of the ocean for a specific type of boat. Breakthrough Listen has searched roughly the equivalent of one large bathtub full of water from a 1.5 billion cubic kilometre ocean. We've barely started, and we've been assuming they communicate by radio. That's a very Earth-centered assumption. A civilization a million years more advanced than ours might find radio waves as primitive as we'd find smoke signals. They might communicate through methods we've never conceived of, using physics we haven't discovered, with signals that our instruments are completely blind to. Or they might not communicate at all, at least not in ways that leak into space. Human civilization produced significant radio leakage throughout the 20th century because we were broadcasting at high power from the surface of a planet without any particular attempt at efficiency, but we're already moving toward tighter, more focused communication technologies. Fiber optic cables, directional satellite communications, encrypted digital signals that look more like noise than structured information. A century from now, Earth might produce far less detectable radio leakage than it did in 1960. Any civilization that went through this same transition, from broadcast radio to highly efficient, tightly directed communication, would gradually become invisible to a civilization trying to listen for their leakage. If the window of radio leakage is only 100 or 200 years, and if civilizations are spread across 100,000 light-years of space, the chances of any two of them overlapping in both time and frequency is actually quite small. We might be surrounded by civilizations that passed through the radio era before we were born, and whose leakage has long since passed us by. The argument here isn't that they're definitely out there and we're just missing them. It's that the absence of a signal in our current search is much weaker evidence for absence than most people intuitively feel. Now let's go to something that I think is genuinely underappreciated in conversations about the Fermi paradox: the concept of the temporal distribution of intelligence. Think about this. Our galaxy is 13.6 billion years old. Stars have been forming throughout most of that time, though the rate has changed. The earliest stars were made of almost pure hydrogen and helium because those were the only elements that existed immediately after the Big Bang. They burned bright and fast and exploded as supernovae, seeding the universe with the heavier elements that everything we see today is made of: carbon, oxygen, nitrogen, iron, phosphorus, silicon. All of these were forged in the hearts of stars and scattered by those explosions. The first generation of stars couldn't have had rocky, Earth-like planets. There wasn't enough silicon or iron to make them. It wasn't until the second and third generations of stars, formed from the debris of earlier stellar explosions, that the raw materials for rocky worlds were abundant enough to build something like Earth. That process took time, billions of years, and it's still ongoing. The universe is still making new stars, still exploding old ones, still enriching the interstellar medium with heavier elements. This means that the conditions for Earth-like planets and Earth-like chemistry have been gradually improving throughout the history of the universe. We may actually be living at a time when conditions are particularly good for the kind of chemistry that produces life. But here's what's interesting about the temporal argument. If conditions for complex life have been improving over time, and if we're at a point in cosmic history where those conditions are, by some measures, near their peak, then we might expect many civilizations to be forming more or less in the same broad era, not simultaneously, not even within 1,000,000 years of each other, but within the same billion-year window. That window is now. We're in it. Which means that if other civilizations are forming, they're forming now, not 5 billion years ago, not in some distant future. The civilizations that might be out there, if they exist, are likely at roughly comparable stages of development, which is both hopeful and frightening. Hopeful, because it means they're out there in our era. Frightening, because it means they haven't expanded across the galaxy yet either, which might mean none of them have been able to. Or maybe it just means none of them have had enough time. Maybe interstellar colonization is genuinely just beginning, and in 1 billion years the galaxy will be full of civilization signatures that today haven't yet made it across the distances. We can't know, but the temporal framing is worth keeping in mind. We're not necessarily late to the party. We might be among the first guests to arrive at a party that's just getting started. Let's talk about something concrete that happened in 2017. Something that genuinely surprised astronomers and sparked serious debate about exactly the kinds of questions we're discussing. In October of 2017, telescopes at the Haleakala Observatory in Hawaii detected an object passing through our solar system on a trajectory that made clear it had come from outside our solar system entirely. The first interstellar object ever confirmed to have entered our solar system. It was given the designation 1I/2017 U1 and named Oumuamua, a Hawaiian word meaning scout or messenger from afar. What made astronomers pay close attention was its behavior. It was accelerating, slightly, but measurably. As it moved away from the sun, it was speeding up faster than gravity alone could explain. The standard explanation for this kind of non-gravitational acceleration is outgassing, the release of gas and dust from an object as it heats up near a star. Comets do this. It produces a rocket-like push, but astronomers watched Oumuamua closely and found no evidence of any outgassing, no visible gas cloud, no dust trail, nothing. Its shape also appeared unusual. Preliminary analysis suggested it was extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar. No natural object we've ever observed in our solar system looks quite like that. Harvard astronomer Avi Loeb, one of the more prominent and controversial figures in the study of Oumuamua, published a paper arguing that the most natural explanation for its anomalous acceleration wasn't outgassing, wasn't any standard cometary process, but might be radiation pressure acting on an extremely thin, flat, sail-like object, like a solar sail, a technology we ourselves have experimented with. If Oumuamua were a thin, flat sheet, maybe a fraction of a millimeter thick, but hundreds of meters across, sunlight alone could push it the way we observed it being pushed. Loeb's paper was controversial. Most astronomers found it premature and preferred natural explanations, including a revised hypothesis that Oumuamua might be made of hydrogen ice, a type of object we've never observed before, but that would explain both its appearance and its acceleration. The honest position is that we don't know what Oumuamua was. We can't go back and study it. It's long gone, heading out of the solar system, unreachable by any probe we could build now. What we do know is that it was unusual, and the fact that the first interstellar object we ever confirmed to observe in our solar system was unusual enough to generate serious scientific discussion about its origin is at minimum worth noting. Most scientists think it was natural, but not all, and the disagreement is genuine, not fringe. Let's go somewhere that most Fermi paradox discussions don't spend enough time. let's go to the question of what the universe's silence tells us about our own future. Imagine for a moment that the Great Filter really is ahead of us, that we are typical, not exceptional, that other civilizations have arisen, developed technology, and then hit whatever the filter is. If that's true, those civilizations are gone. We can't learn from them directly. We can't ask them what happened, but we can look at our own situation and ask which of the problems we face most closely resembles the kind of challenge that would reliably end a civilization. There are a few candidates that come up repeatedly. Nuclear war we've already mentioned. The logic here is grimly simple. Every civilization that develops nuclear weapons has, in a sense, invented a tool that could end its own story. The challenge of preventing nuclear war isn't just political, it's existential, and the record so far, both the near misses and the ongoing proliferation of nuclear arsenals, suggests that managing this threat is genuinely hard. We've been lucky, specific individuals, in specific moments, made choices that prevented escalation. Luck doesn't scale. It doesn't hold indefinitely. Climate change is a slower version of the same problem, a civilization that alters its planet's atmosphere in ways that take centuries to manifest, and that requires coordinated sacrifice from billions of people across dozens of competing governments, faces a collective action problem of extraordinary difficulty. We know what we're doing. We have the science. We even have the technology to address it. What we lack so far is the coordination. That gap between knowing and doing at a species level might be a standard feature of intelligent civilizations, and it might be lethal. Engineered pandemics. As biotechnology becomes more capable and more accessible, the threshold for creating a pathogen capable of causing a pandemic drops. The COVID-19 pandemic that emerged in late 2019 and spread through 2020 and beyond demonstrated how vulnerable a globally connected civilization is to a novel infectious disease, even a relatively modest one by the standards of history. A deliberately engineered pathogen, optimized for transmissibility and lethality by someone with sufficient technical capability and sufficient motivation, represents a risk profile that our institutions were not designed for and have not fully adapted to. Artificial superintelligence, as we mentioned earlier, the development of a machine intelligence that surpasses human cognitive capability in every domain, is by most accounts something that will happen in this century if current trends continue. The alignment problem, ensuring that such a system remains oriented toward human flourishing rather than its own goals, is real and is not solved. It might not be solvable with our current tools and understanding, and an unaligned superintelligence, depending on its goals, could render human civilization as incapable of continuing as we render the goals of an ant colony irrelevant when we build a road through their territory. Not out of malice, just irrelevance. None of these risks is certain to be terminal, but each of them has the structural property that the Great Filter requires. It becomes increasingly likely as a civilization's technology develops, and if it hits, it tends to hit permanently. Now let's talk about something that adds another layer of complexity. What if the question of life in the universe isn't just about civilizations? What if the real question is about consciousness, about the subjective experience of being aware of one's own existence? This is a philosophical dimension of the Fermi paradox that often gets left out of the scientific discussion, but I think it deserves attention. We tend to assume that if life is common, intelligence is a natural consequence, that evolution, given enough time, tends toward complexity, and complexity tends toward awareness. But that assumption isn't obviously true. Intelligence as we know it, the kind that builds radio telescopes and writes philosophy, might not be the natural endpoint of evolution at all. It might be a weird detour. Consider what evolution actually selects for. Not intelligence per se, survival and reproduction. For most of Earth's history, The strategy that worked best for most organisms was simple: eat enough, avoid being eaten, reproduce. The vast majority of successful species on Earth are not intelligent in any meaningful sense. Bacteria are extraordinarily successful by evolutionary standards. Beetles are incredibly diverse and numerous. Sharks have been essentially unchanged for 400 million years, which tells you something about how well their current design works. Intelligence emerged in our lineage and in a handful of other animal lineages in modified forms, and it's clearly been useful. But there's no obvious reason why evolution would inevitably produce the specific kind of recursive, language-based, tool-using, self-reflective intelligence that we have. It might be a lucky combination of evolutionary pressures that happen to converge in just the right way on just the right primate. Other lineages have produced intelligence that's clearly not like ours. Crows and other corvids are remarkably intelligent for birds. Octopuses are cognitively sophisticated in ways that continue to surprise researchers. Dolphins and great apes show various capacities for learning, problem-solving, and even rudimentary language. But none of them have built radio telescopes. None of them have developed a technology base that changes their planet's chemistry. None of them have reached the specific threshold that the Fermi paradox requires. Maybe that threshold is genuinely rare. Maybe the combination of intelligence, social organization, fine motor control, fire, and whatever psychological and cultural factors make science and technology possible is a narrower gate than we assume. Maybe it requires not just a smart brain, but a particular kind of smart brain, embedded in a particular kind of social structure, on a particular kind of planet, at a particular point in a planet's developmental history. We're back again to the rare Earth argument, but now applied not just to life in general, but to the specific kind of life that builds civilizations. Here's another angle on the same question. Let's talk about the anthropic principle, because it casts everything we've said in a different light. The anthropic principle, in its weak form, is simply the observation that any universe we observe must by definition have the properties necessary for us to exist to observe it. If the physical constants of the universe were even slightly different, if gravity were a bit stronger, if the strong nuclear force were slightly weaker, if the cosmological constant had a different value, then atoms wouldn't form, or stars wouldn't form, or they'd burn out too quickly, or any of a dozen other things would go wrong that would prevent the development of complex chemistry and life. The fact that we observe a universe with life-permitting constants doesn't tell us those constants are fine-tuned for life. It just tells us that the universe we observe is the kind that can produce observers. The anthropic principle doesn't resolve the Fermi paradox, but it does something subtle. It cautions us against certain kinds of reasoning. Specifically, it warns us that the fact that life exists on Earth doesn't tell us how likely life is in general, because we can only ever make this observation from a life-bearing planet. And the fact that intelligent life arose on Earth doesn't tell us how likely intelligence is in general, because we can only ever make this observation from a planet where intelligent life arose. We are, in every possible universe we could observe, the survivors, the ones who made it. And the survivors always see their own survival as meaningful, even when it was just luck. This doesn't mean our existence is meaningless. It means we need to be careful about using our own existence as evidence that existence is common. It's a subtle but important distinction, and it's one that philosophers of science have been wrestling with for decades without a fully satisfying resolution. Let's go somewhere unexpected for a moment. Let's talk about silence as a thing in itself, separate from the Fermi paradox and its specific scientific arguments. We've been talking about the silence from the sky as a problem to be explained, but there's another way to sit with it. The universe is genuinely very quiet, not just in terms of radio signals from civilizations, in terms of any obvious large-scale organization or meaning. The universe doesn't have a voice. It doesn't send messages. It just does what physics tells it to do, with no commentary, no signal that says this is what you're supposed to understand, no note saying good job or you're on the right track. Just quarks and fields and forces and time doing what they do indifferently and precisely. Humans have always had trouble sitting with that silence. Every major religious tradition in history has been an attempt to hear something in it, to find a voice in the void that says something meaningful and personal. Whether you find that impulse beautiful or misguided, it's universal. We are not comfortable with the idea that the universe doesn't know we exist. The Fermi paradox is, in a way, the scientific version of that same ancient discomfort. We've built instruments capable of searching for voices in the void, and we haven't heard any, and we want to know why. Not just because it's scientifically interesting, though it is, but because the answer matters to how we understand ourselves. If we're not alone, we're part of a community, even if we've never met anyone else in it. If we are alone, we're something different, something singular, something that carries a weight we don't fully know how to hold. Let's talk about what a serious detection would actually look like. If we did receive a confirmed signal from another civilization, what would happen? The SETI Institute has a protocol. It's called the Rio scale, and it's a framework for evaluating the significance and credibility of a claimed detection. It assigns a score from 0 to 10, where 0 means no significance and 10 means a verified, world-altering detection of intelligent extraterrestrial origin. Most alleged detections in history have scored 0 or 1. The WOW signal has been assessed at about a 4 or 5 depending on who's evaluating it. If a signal scored a 7 or higher and was confirmed by multiple independent observatories, the protocol calls for broad notification of the astronomical community, government authorities, and the international community before any public announcement. The challenge is that in the modern information environment, with real-time global communication and social media, the idea that such a discovery could be contained and managed before public announcement is optimistic at best. But setting aside the practical challenges of announcement, think about what a confirmed detection would mean, not in the abstract but specifically. A signal that was definitively artificial, that encoded information, that came from a specific direction and a specific distance, would change what it means to be a human being on Earth in a way that nothing in the history of our species has quite prepared us for. Every philosophical system, every religious tradition, every political ideology, every ethical framework would have to reckon with the existence of a second intelligence in the universe. Not in a science fiction way where we immediately start worrying about invasion, but in a deep, slow, structural way. All of our frameworks for understanding our place in the universe were built on the assumption, sometimes explicit, but mostly just background, that we are the only ones. Remove that assumption, and things shift in ways that are genuinely hard to predict. How would that affect how we treat each other? If we're not alone, if there are other minds out there looking back at the same universe we're looking at, does that change how we perceive our own internal conflicts? Do wars between humans seem smaller against the backdrop of a universe full of alien civilizations? Or does the competition for resources and survival become more intense as we realize we're not just competing with each other but potentially with others we can barely imagine? We don't know. We've never been in this situation. We have no historical analogy for it. The closest thing might be the period when previously isolated cultures first made contact with each other, and those experiences ranged from transformative to catastrophic depending on the circumstances. But even those contacts were between beings who shared biology, shared Earth, shared time. Contact with something that doesn't share any of those things is genuinely unprecedented territory. Let's talk about the next 100 years, because I think they're going to be decisive in ways we can't quite articulate yet. In the next 100 years, we are almost certainly going to either find evidence of life beyond Earth or understand clearly enough why we haven't found it yet to know what that means. The James Webb Space Telescope, which launched in December 2021 and has been producing extraordinary results, is the first instrument capable of analysing the atmospheres of some nearby exoplanets in enough detail to look for biosignatures. Biosignatures are chemical signatures in an atmosphere that would be hard to explain without biology. Things like oxygen at high concentrations, or methane in combination with oxygen, which would react together and disappear quickly in the absence of something constantly replenishing both of them. Life is the obvious replenisher. Webb can't do this for most exoplanets. The engineering required to tease out atmospheric information from a small rocky planet orbiting a distant star is at the very edge of what the telescope can do. But for a small number of nearby planets orbiting M-dwarf stars, planets like those in the TRAPPIST-1 system, which are 40 light-years from Earth, and which contain at least 3 planets in the habitable zone, it might be possible to get some atmospheric data. 40 light-years, to put it in perspective, is about 235 trillion miles. If you shrank the entire distance between New York and Los Angeles to the length of a golf tee, the scale of that model would make the distance to TRAPPIST-1 approximately the length of a 30-kilometer hiking trail. We're not going there anytime soon, but we can look at it. The next generation of telescopes currently in development will do better. The Habitable Worlds Observatory, a concept under development by NASA for launch sometime in the 2040s, is designed specifically to image Earth-like planets around Sun-like stars and analyze their atmospheres for signs of life. If we build it, and if it works, and if we're lucky, we might, within the lifetime of people reading this, have our first real evidence of biology beyond Earth. Or we might search the nearest 1,000 stars carefully and find nothing. That would be a different kind of answer, but still an answer. The Mars missions of the coming decades are also relevant. Various space agencies have plans for robotic exploration of Mars's subsurface, where any surviving liquid water would likely be found. If there is or ever was life on Mars, the subsurface is the most likely place to find it. A positive detection there would be, as we said, transformative. Not just scientifically but philosophically. It would tell us that life arose independently twice within our own solar system, in the same small corner of one galaxy, which would imply very strongly that it's everywhere. Let's sit for a moment with the specific loneliness of this question. Not the abstract philosophical version, but the personal one. When you go outside on a clear night and look up, what you're seeing is not decoration. Those are real places, real stars, each one a physical object, a nuclear furnace, burning hydrogen into helium at pressures and temperatures so extreme that the numbers don't have normal meanings anymore. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away, at the speed of the fastest spacecraft humanity has ever launched, the New Horizons probe that flew past Pluto in 2015. A journey to Proxima Centauri would take about 78,000 years. 78,000 years ago, our species was crossing out of Africa. We were painting the first cave paintings, burying our dead, making music with bones and stones. The entire known history of human civilization, from the first written word in Mesopotamia around 5,000 years ago to right now, represents just 6.4% of the time it would take our fastest spacecraft to reach the nearest star. And Proxima Centauri is next door. The next nearest star systems are farther. Most of the stars visible on a clear night are hundreds or thousands of light-years away. The Andromeda Galaxy, the nearest large galaxy to ours, is 2.5 million light-years away. At New Horizons speed, a journey there would take about 46 billion years, which is more than 3 times the current age of the universe. The scale of the separations involved is such that even if the universe is full of civilizations, even if every star system has a thriving civilization orbiting it, we would never know, we would never meet, we would never communicate in anything resembling real time. The light from a civilization around Proxima Centauri would take 4.2 years to reach us. If we sent a message and they replied, we'd receive the reply 8.4 years after we sent it. For a star 1,000 light-years away, a two-way conversation would take 2,000 years. The universe is not built for communication. It's not built for connection. Its fundamental physical constant, The speed of light enforces a separation between things so absolute and so permanent that two civilizations in adjacent star systems might spend all of recorded history trying to have a conversation and never get through more than a few exchanges. This is one of the more genuinely unsettling realizations you can have about the universe. Not that it's hostile, just that it's structured in a way that makes cosmic community, in any form we'd recognize as community, essentially impossible. Even if everyone is out there, even if the galaxy is full of voices, the speed of light means we can never really speak to each other in any way that feels like speaking. Let's go back to the Great Filter one more time, because there's a nuance we haven't explored yet. The idea that the filter might not be a single thing. Most discussions of the Great Filter treat it as one big barrier, one specific transition that's improbably hard and that most civilizations fail to get through. But what if the filter is actually a series of smaller barriers, each individually manageable but collectively very effective at reducing the final population of spacefaring civilizations? Think of it as a funnel. A wide funnel narrows through a sequence of constrictions, each one removing a fraction of the flow. If you start with 1 trillion planets and filter out 99.9% at each of 10 steps, you end up with 1 trillion times 0.001 to the 10th power, which is a very small number. Step 1. Star stability. Maybe 30% of stars are stable enough and long-lived enough to support planetary systems that persist long enough for complex life. Step 2. Rocky planet formation. Maybe 20% of stable stars have rocky planets in habitable zones. Step 3. Water retention. Maybe 30% of those planets retain liquid water over billions of years. Step 4. Life origin. Maybe 10% of water-bearing habitable planets develop life. Step 5. Eukaryotic complexity. Maybe 1% of life-bearing worlds develop complex cells. Step 6. Multi-cellular life. Step 7. Intelligence. Step 8. Civilization. Step 9. Technological capability. Step 10. Survival past the technological threshold. Multiply those probabilities together, and by the time you reach step 10, the number of surviving civilizations might be very, very small. Even if every individual step has what seems like a reasonable probability, the funnel does its work not through one dramatic bottleneck, but through the accumulated weight of many modest ones. This model is actually somewhat hopeful, in a perverse way, because it doesn't require a single catastrophic filter. It just requires that life and civilization are hard in many different ways simultaneously, which is something we can actually observe and test. We can look at each step and try to understand how common it is. Now let's talk about one of the more creative and underexplored hypotheses. The idea that the Fermi paradox might be solved, not by civilizations being absent, but by civilizations going inward rather than outward. This is sometimes called the simulation hypothesis or the virtual transcendence hypothesis. The idea is that any sufficiently advanced civilization will at some point develop technology capable of creating a subjective experience, a simulated reality, that is indistinguishable from or superior to physical reality in every way that matters to the beings experiencing it. And once that threshold is crossed, the civilization might collectively choose to explore the simulation rather than physical space. They would go inward, not outward, not through space but into their own created worlds. If this is true, then the silence of the sky isn't because civilizations are absent or dead. It's because they became something we don't recognize and stopped caring about physical expansion. They're not broadcasting because they're busy, not busy in a way we'd understand, busy in a way that has no external signature. The physicist and futurist Michio Kaku has argued that once a civilization reaches a sufficiently advanced level, it would classify its activities not by physical expansion, but by energy consumption. A Type 1 civilization, on the scale invented by physicist Nikolai Kardashev, controls the energy of its home planet. A Type 2 civilization controls the energy of its star. A Type 3 civilization controls the energy of its galaxy. We're currently at roughly 0.73 on this scale. We're still a Type 0 civilization. We haven't even mastered our own planet's energy budget. The gap between us and a Type 2 civilization is something like the gap between a single candle and an entire city's worth of electricity. The gap between us and a Type 3 civilization makes the first gap look trivial. But here's the interesting thing about the virtual transcendence hypothesis. A civilization that chose to go inward, to live in simulated realities of its own making, might not need to consume the energy of its star or its galaxy. It might consume only what it needs to run the simulation. And if its simulation is rich enough and satisfying enough, that might not be very much at all. Such a civilization would be nearly invisible from outside. It's a strange and somewhat melancholy possibility that the universe might contain countless civilizations who have all, independently, looked at the enormous cold distances between stars and the tiny warm richness of a well-constructed inner world, and chosen the inner world, not because of fear, because the inner world is simply more interesting and more accessible. Is that what's waiting for us? A threshold where physical space becomes irrelevant because inner space is limitless? We don't know. We can't know. But it's at least as coherent an answer to the Fermi paradox as any of the others. Let's go back to Earth for a moment. Let's talk about what's actually happening in the concrete world of research, because the field is moving fast. One of the most significant recent developments in the search for life is the shift toward looking for biosignatures in planetary atmospheres using spectroscopy. The way this works is elegant. When light from a star passes through the atmosphere of a planet orbiting that star, different molecules in that atmosphere absorb specific wavelengths of light in predictable ways. Each molecule has a characteristic absorption pattern, like a fingerprint. By looking at the starlight and seeing which wavelengths are missing, astronomers can identify which molecules are present in the atmosphere. We've been detecting molecules in exoplanet atmospheres for years. We found water vapor, carbon dioxide, methane, sodium, potassium. But the holy grail is something called the biosignature, a combination of molecules whose only plausible source is biology. Oxygen is a good candidate. It's so chemically reactive that it should combine with rocks and other elements very quickly. Without constant replenishment, it disappears within millions of years. On Earth, the only thing replenishing it at the massive scale we observe is photosynthesis, billions of organisms converting carbon dioxide and water into oxygen and sugar every day across the entire surface of the planet. Find an atmosphere with a lot of oxygen in it and you've got a serious candidate for life. But oxygen alone might not be enough. There are abiotic processes that can produce oxygen in modest quantities. To be confident, you'd want oxygen plus methane together because those two gases react and destroy each other, so finding both in the same atmosphere strongly suggests something is continuously generating both. On Earth, both are generated by life. The James Webb Space Telescope has already begun doing this kind of analysis on TRAPPIST-1 planets. The results so far are intriguing but not definitive. The planet TRAPPIST-1b doesn't appear to have a thick carbon dioxide atmosphere, which rules out some scenarios. The planet TRAPPIST-1c shows signs that might suggest a rocky, bare surface rather than a lush biosphere. But we're still early in the analysis, and the data is difficult to interpret with confidence. The next few decades of telescope development will dramatically improve our ability to do this, and at some point, possibly within our lifetimes, we'll have the tools to look at the atmospheres of hundreds of nearby rocky planets and ask, directly, whether they carry the chemical signatures of life. That moment, when we can say definitively yes, that planet has something biological happening on it, or no, after checking 500 planets with the right conditions, none of them show signs of life, will be one of the most important moments in the history of science. Let's think about what it would mean if we searched those 500 planets carefully, found nothing, and then searched 5,000 more and found nothing, and then built better telescopes and searched 50,000 and found nothing? At what point does the absence of evidence become evidence of absence? That's a genuinely contested scientific question, and the answer depends on what you think the prior probability of life is. If you go into the search believing life should be very common, a lot of negative results are required to change your mind. If you go in believing life might be rare, even a modest number of negative results is meaningful. What most scientists would say is that we can't claim to have a negative result until we've searched a large and representative sample of habitable planets with instruments capable of detecting the kinds of biosignatures we know to look for. We're not there yet. We're orders of magnitude short of that sample size. But we're getting closer, and the conversation about what a genuinely compelling negative result would look like is worth having before we get the result, not after. Now let me bring something up that I find genuinely underappreciated in this conversation. The question of what we mean by intelligence and whether we might be looking for the wrong thing. Everything about the Fermi paradox assumes that other civilizations, if they exist, will be recognizable to us, that they'll have technology, that they'll broadcast radio waves, that they'll build large physical structures or consume energy at scales we can observe, that they'll do things we can detect and interpret as intentional and artificial. But why should any of that be true? Intelligence on Earth took one particular form. The specific path from primate to language to science to technology is one path. It's the path that happened here, in this lineage, on this planet, in this era. But there's no reason to think it's the only path that evolution can take towards something we'd call intelligence. And there's no reason to think that all paths lead to something that looks even vaguely like ours. Octopuses are cognitively sophisticated, but their intelligence is distributed across their arms, each of which operates semi-independently. They don't have a centralized brain in the way we do. They're also solitary. They don't cooperate in the sustained way that human social structures allow. Even if their intelligence were considerably greater than it is, would they build civilizations? Would they develop science? Would they transmit radio waves? The intelligence of social insects like ants and termites is collective and distributed, a property of the colony rather than any individual. The kind of problem solving and construction they accomplish, including climate-controlled mounds meters tall, fungal agriculture, and coordinated defense, is extraordinary by any measure. But it's not leading to telescopes. The architecture of insect cognition simply doesn't produce that kind of output. Dolphins are intelligent by many measures. They have large brains, they communicate, they cooperate, they play. They have what appears to be culture, localized behavioral traditions passed from generation to generation, but they don't have hands. They live in water. The specific combination of cognitive capability and physical manipulation that allows technology, making and using tools to alter the environment in systematic and accumulating ways requires a very particular body plan along with the brain. All of this suggests that the pathway from life to civilization is more constrained than just evolve enough intelligence. It might require a very specific combination of cognitive capacity, social structure, physical manipulation, environmental conditions, and chance. And all of those requirements stacking together might produce something genuinely rare. If intelligence elsewhere took forms that didn't produce technology, or produced technology that looks nothing like ours, we might not recognize it as intelligence at all. We might detect a planet full of sophisticated, aware, experiencing beings and classify their world as a sterile, biology-free rock, because their version of civilization left no footprint we know how to read. Let's talk about something that doesn't get enough attention in these conversations: the question of time. Not the age of the universe, we've talked about that. The question of how long civilizations actually need to do things, and how those timescales interact with the timescales of detection. Our civilization has been broadcasting detectable signals into space for about 120 years. The oldest of those signals have traveled 120 light-years. Within that 120 light-year sphere, there are about 15,000 star systems, but the electromagnetic signal has been spreading in all directions at the speed of light, growing thinner and fainter as it spreads across a larger and larger volume of space. By the time it reaches even 50 light-years from Earth, the signal is so faint that it would require a radio telescope the size of a continent to detect it against the background noise of natural astrophysical sources. Our own detection capability for signals coming from another civilization is also limited. The most powerful radio signals we've ever deliberately beamed into space, intentionally aimed at specific star systems, could potentially be detected by a civilization with our current technology at distances of maybe a few hundred light-years. For unintentional leakage, the kind that just spills from our broadcast infrastructure, the detection range is much shorter, maybe a few dozen light-years at best. What this means is that the sphere of mutual detectability, the range within which two civilizations with our capabilities could detect each other, is quite small compared to the size of the galaxy, and the timeframes involved, civilizations being detectable for maybe a few hundred to a few thousand years before they transition to tighter, quieter communication technologies, mean that the window of detection is narrow. Even if the galaxy is full of civilizations, most of them at most points in their development would be invisible to each other. They'd exist in isolation, not because of choice or hostility or some cosmic law, but simply because the physics of detection across interstellar distances is brutally unfavorable unless you're actively trying very hard to broadcast, and unless someone is actively searching in exactly the right direction, at exactly the right frequency, at exactly the right time. The cosmic haystack is enormous. The needles, if they exist, are small and quiet and moving. I want to take a moment here and just let us sit with what we've been building, because I think there's something important in the shape of this whole inquiry that's worth naming. We started with size, the sheer enormous scale of the universe. We moved to the Drake equation, the systematic attempt to quantify what that scale means for life. We looked at the Fermi paradox, the gap between what the math suggests and what we observe. We walked through the rare Earth hypothesis and its long list of requirements. We arrived at the Great Filter and its two possibilities, behind us or ahead. And then we started going inward, from the galaxy to the star, to the planet, to the chemistry, to the cell, to the organism, to the civilization. Each step a potential filter, each step a place where almost everything gets sorted out before it can reach the next level. What I find genuinely interesting about all of this is not the specific answer to any one of these questions, but the overall shape of the inquiry. The question of whether we're alone is at its heart the question of how hard it is to be us, how many things had to go right, how many near misses there were, how many steps along the path from hydrogen gas to philosophy required just the right conditions, just the right timing, just the right luck. And the more carefully we look, the more steps we find, the more requirements we uncover, the more ways the story could have gone differently, and almost certainly went differently almost everywhere else. That's not a pessimistic conclusion. It might actually be the most important thing science has ever told us about ourselves. Not that we're made of the same stuff as the stars, though we are, and that's beautiful. But that getting from that stuff to us required something genuinely improbable, something that the universe doesn't just do automatically given time and space. We are not a default outcome, we're an exception. And if exceptions are rare, then we matter in a way that feels almost too large to hold. Let's talk about one more possibility, one that's genuinely strange and that doesn't fit neatly into any of the other categories. The idea that the universe might be stereo, not by chance, but by design, or, more precisely, that the universe might be at a stage in its development where life is just beginning to become possible. Astrophysicist David Spiegel and biochemist Edwin Turner published a paper arguing that the speed with which life arose on Earth, within the first 800 million years or so, actually tells us very little about the intrinsic probability of life originating. Specifically, they argue that we're subject to a selection bias. Given that we exist, we're guaranteed to find ourselves on a planet where life arose quickly enough for us to evolve. The rapidness of Earth's abiogenesis might reflect selection effects, not the general probability of life's origin. But there's a more radical version of this argument, associated with scientists like Charles Lineweaver and others who study what's sometimes called cosmic evolution, or cosmological natural selection. The argument is that the conditions for life, the abundance of the right elements, the stability of stellar environments, the prevalence of long-lived habitable planets, have been improving throughout cosmic time. The universe is getting better at making life. We might be among the first waves of complex life to arise, not because we're extraordinarily lucky, but because we're early. In this model, the Great Filter isn't a single event or a catastrophic challenge. It's simply timing. The universe is 13.8 billion years old, and for most of that time the conditions for complex life weren't quite there yet. The first stars were made of hydrogen and helium. The heavy elements needed for rocky planets and organic chemistry took billions of years to accumulate through cycles of stellar birth and death. The galaxy needed time to settle into a stable configuration. Early on, supernovae and gamma-ray bursts and black hole mergers were more frequent, bathing the young universe in radiation hostile to complex chemistry. If this is right, and the evidence is at least consistent with it, then we might be living in the era when life first becomes genuinely common in the universe. The first civilizations are arising now, in this billion-year window, because this is the first billion-year window when conditions are broadly favorable. The galaxy isn't empty because life is rare. It's quiet because it's just beginning. And if that's true, then the question of what civilizations do next, how they manage their technology, whether they survive their great filters, whether they expand or go silent or transcend, is a question whose answer will be written over the next few billion years, not by civilizations long gone, by civilizations like ours, just getting started. Let's think about what all of this means for how we live. Right now, on this particular Tuesday or Thursday morning, with everything we've just talked about sitting in our heads, if the Great Filter is behind us, we are genuinely precious. We are the thing that the universe spent 13.8 billion years building toward. Not intentionally, not purposefully, but through the accumulated operation of physics and chemistry and time. We are the place where the cosmos became aware of itself. Everything we do matters, not in a supernatural sense, but in a real, physical sense. We are the only witnesses, the only recorders, the only beings anywhere in this galaxy, as far as we know, who understand what's going on. The dinosaurs were here for 165 million years. That's about 35 times longer than the entire duration of our genus. They never understood what they were. They were magnificent and terrible and wildly successful, and then they were gone, and nothing they ever did or saw or felt was retained or understood. It just happened and then it was over. 65 million years of dark and silence on a planet that had briefly been full of extraordinary animals, and no one knew. We have an opportunity that no other life form on Earth has ever had. We can understand our situation. We can see the whole scope of it. We can look back 13.8 billion years and forward into a future that might extend for trillions of years if we manage it right. We can choose in a way that no other species ever has what to do with that understanding. That's not a burden, or at least it doesn't have to be only a burden. It's also a kind of privilege. The ability to understand something fully is not a small thing. It might be the rarest thing in the universe. If the Great Filter is ahead of us, then nothing changes the immediate urgency but the framing of it. We face existential risks, real ones. Nuclear, biological, technological, ecological. We've been in the shadow of some of them for decades, and will be in the shadow of others very soon. The question of whether we navigate them successfully isn't academic. If the Fermi paradox has anything to tell us, it's that civilizations can fail to make it through. The silence of the sky is, among other things, a statistical statement about how hard the far side of the filter is. But knowing that doesn't make failure inevitable. It makes the effort more urgent. If most civilizations fail the test that's coming, being one of the few that doesn't isn't just survival, it's the whole story. It's what makes the universe's long labor mean something. Let's talk about something that's become more concrete in the last few years, and that I think is genuinely changing the texture of this conversation. Because the Fermi paradox was, for most of its history, a thought experiment, a fascinating puzzle with no real empirical traction. We couldn't search much. We couldn't observe exoplanet atmospheres. We couldn't even confirm that other stars had planets at all until 1992, when the first confirmed exoplanet was detected orbiting a pulsar, a dead star. The first confirmed exoplanet orbiting a sun-like star wasn't found until 1995. So for most of the decades when scientists were wrestling with the Fermi paradox, they were doing it in an observational vacuum. We knew the question was real. We didn't have the tools to start answering it empirically. That has changed dramatically in the last 30 years, and it's changing faster now than ever before. The Kepler Space Telescope, launched in 2009 and retired in 2018, changed our picture of the galaxy more than almost any instrument before it. By staring at a fixed patch of roughly 150,000 stars and watching for the tiny periodic dimming caused when a planet crosses in front of its star, Kepler found over 2,600 confirmed exoplanets and thousands more candidates. Its data told us something profound. Planets are not rare anomalies. They're the normal condition. Almost every star has at least one planet. Most have several. The galaxy, we now know with confidence, is full of worlds. Before Kepler, this was an assumption. After Kepler, it's a measurement. And that measurement changes the weight of the Fermi paradox, because now we know the first factor in Drake's equation with genuine confidence. Stars have planets. That part is settled, which means the silence is even stranger than it was before, because the opportunities for life to arise are even more numerous than we suspected. The TESS satellite, launched in 2018 as Kepler's successor, extended that survey across the whole sky. It's been finding exoplanets faster than astronomers can follow up on all of them. By the time we're having this conversation, thousands of confirmed exoplanets are known, and the estimates for the total number of planets in the galaxy keep growing. We're likely looking at trillions of worlds out there, not billions, trillions. And many of them are in the right places. The TRAPPIST-1 system that we mentioned earlier, 40 light-years away, has at least 3 planets in its habitable zone. 3 planets where liquid water on the surface is at least theoretically possible, all orbiting the same star, all within a tiny fraction of the distance it would take any probe we build today to cross. If we could study those planets with the tools we're building, we'd be looking at 3 separate tests of the hypothesis that habitable zones produce life, 3 chances to see a biosignature or not, 3 data points instead of 1. That's the world we're entering, a world where the Fermi paradox stops being purely philosophical and starts accumulating empirical weight. Either we find something and the story goes one way, or we find nothing again and again across thousands of carefully studied worlds and the story goes another. Either outcome is transformative, but the willingness to actually look, to actually run the test, to actually confront the question with instruments and data rather than intuitions is new. We're living in the era where it starts to become answerable. Now I want to spend some time on something that often gets skipped. The specific physical and chemical story of how Earth became the planet that it is. Because I think if you understand that story, the rare Earth hypothesis stops feeling like a list of requirements and starts feeling like a list of miracles. The story begins about 4.6 billion years ago, in a cloud of gas and dust orbiting a newly formed sun. The The cloud was the raw material of the solar system, and it was already rich in heavy elements because the sun formed in a region of the galaxy where earlier generations of stars had died and scattered their contents. The collapse of that cloud under its own gravity produced the sun at its center and left a rotating disk of material surrounding it. Over tens of millions of years, that disk of material clumped together. Dust grains stuck to each other, small clumps grew into larger ones collided and merged. Eventually, in the inner part of the disk, several rocky protoplanets had formed, and then the collisions between them became catastrophic, planet-scale impacts rather than simple mergers. One of those impacts, roughly 4.5 billion years ago, involved a proto-Earth and a body roughly the size of Mars. The collision was not a head-on impact but a glancing blow at an oblique angle. The colliding body, which we call Theia, was essentially destroyed. The Earth was partially vaporized, and its material mixed with Theia's. The resulting cloud of molten rock and vapor surrounding the Earth began to cool and coalesce. Most of it fell back to Earth, but a significant amount stayed in orbit, and over a few thousand years it condensed into the Moon. The evidence for this giant impact hypothesis is compelling. The Moon has a composition very similar to Earth's mantle, which makes sense if much of the Moon's material came from the outer layers of the Earth. The Moon has very little iron relative to Earth because the iron core of both the proto-Earth and Theia had already sunk to the center before the impact, and the impact material came mostly from the mantles. The Moon has almost no water, which makes sense if it formed from hot, vaporized material, in which volatile compounds like water were mostly driven off. The Moon's formation wasn't an afterthought. It wasn't a decoration. It was a consequence of a specific kind of impact at a specific time in the solar system's early chaotic history, and it produced a companion whose gravitational influence on Earth has been, over billions of years, profoundly stabilizing. Without that impact happening in exactly the way it did, Earth's axial tilt would have wobbled chaotically, its climate would have been far less stable, and the long, relatively predictable seasons that life on Earth has evolved to navigate would have been replaced by wild, unpredictable swings. Whether complex life would have had time to develop and persist through those swings is genuinely uncertain. The early Earth, after the Moon formed, was a very different place from what we know now. The surface was covered in magma oceans. The atmosphere was thick and toxic, full of hydrogen, methane, water vapor, carbon dioxide, and ammonia. There was no oxygen. There was no ozone layer to protect against ultraviolet radiation. The bombardment from space continued as leftover debris from planet formation rained down constantly. And then, somehow, in the middle of all of that, life began. We don't know exactly when. The earliest possible evidence of life on Earth comes from carbon isotope ratios in ancient zircon crystals, some of which are 4.1 billion years old. That would mean life began within 400 million years of Earth's formation, during a period called the Late Heavy Bombardment, when the inner solar system was still being pelted by asteroid and comet impacts. If life started during the bombardment and survived it, it's a sign of remarkable resilience. Or it started and ended repeatedly until it finally took hold for good. The first clear fossil evidence of life is about 3.7 billion years old. Structures in ancient rocks in Greenland called stromatolites, layered mats built by microbial communities, leave a physical signature that ancient biology clearly created. 3.7 billion years of life on Earth, almost as long as Earth itself. And for the vast majority of that time, life was entirely microbial. Single cells, living and dying, evolving slowly, covering the planet in an invisible film of biology but producing nothing we'd call complex. 3 billion years of bacteria, just to sit with that. The entire length of time from the first life on Earth to the first animals is longer than the current age of the universe minus the time the universe existed before Earth formed. It's a very long time, and for all of that time, nothing happened that would be visible from space. No structures, no chemistry detectable from a distance, just a thin biosphere of microbes, quietly cycling carbon and sulfur, slowly, imperceptibly changing the atmosphere. What broke the stalemate? What triggered the transition from a microbial world to a world of complex animals? Partly it was the gradual accumulation of oxygen in the atmosphere, driven by billions of years of cyanobacteria performing photosynthesis. About 2.4 billion years ago, what's called the Great Oxidation Event transformed Earth's atmosphere from one with almost no free oxygen to one with a modest but growing amount. The oxygen was toxic to many of the microbes that had thrived in the anaerobic world before it. There was mass extinction on a microbial scale, but the oxygen also made new metabolic strategies possible, including the kind of high-energy cellular respiration that complex multicellular life would eventually need to power brains and muscles and immune systems. The timeline matters. It took 2 billion years of biology on Earth before oxygen started accumulating in the atmosphere. Another 500 million years before complex animals appeared in the fossil record. Another 500 million years of animal evolution before one lineage of primates started using language and building things. The process is long, the requirements are specific, the conditions had to be just right, and they had to stay just right for billions of years. I want to take one more detour, because there's a dimension of the Fermi paradox that we haven't fully explored. The question of what we would even do if the answer turned out to be that we're not alone. Not in the abstract, but concretely. What changes? The answer might be less than you'd expect in some ways, and more in others. In purely practical terms, the day-to-day life of most people on Earth would not change immediately in response to a confirmed detection of extraterrestrial intelligence. Wars would not stop. Markets would not collapse. People would still need to eat, work, and pay rent. The rhythms of ordinary life are surprisingly resilient to even extraordinary news. There's a version of a SETI detection announcement that goes, "Breakthrough signal confirmed, world reacts with excitement and debate, life goes on, scientists study the signal." But the slower, deeper changes might be more significant. The categories through which we think about ourselves and our situation would shift. The assumption that we are the only minds in the cosmos, an assumption so deep in most cultures that it's rarely even articulated, would be gone. What fills its place is uncertain. Some religious traditions would find the detection vindicating. If God or the universe or the force or whatever framework you use created minds, finding that creation elsewhere is consistent with that framework, even amplifying of it. Other traditions would find it destabilizing, particularly traditions that place humanity's relationship with the divine in a singular and central role. The political and philosophical implications might run even deeper. Our entire system of ethics, from individual rights to international law to our moral consideration of animals, is built around human beings as the primary unit of moral consideration. With confirmed knowledge of another intelligence existing somewhere in the universe, even one we could never visit or communicate with in real time, the question of how to extend moral consideration beyond the human would become urgent rather than hypothetical. And the question of what we say back, if we detect a signal that contains information, would be one of the most consequential decisions our species has ever faced. Who decides? A single nation? A scientific body? The United Nations? Every human being alive simultaneously through some global referendum? There is no established process for this. The treaties and international agreements that govern things like the launch of nuclear weapons have no equivalent for the transmission of a response to an alien signal. We would be making it up as we went under enormous pressure with the most consequential possible stakes. It's a decision that would define our species for as long as we survive as a species. Here's something that I think deserves to be said plainly, without drama, but without flinching either. The possibility that we are completely alone is not just scientifically interesting. It is, at the level of our moment in history, politically and ethically urgent. Because if we are alone, or even if we are just functionally alone, the only intelligent beings in a range so large that contact with others is practically impossible, then the survival of human civilization becomes the survival of intelligence in the cosmos. There is no backup. There is no other experiment running somewhere that could carry the torch if ours goes out. There is just us. And we are currently treating our civilization with something less than the care that status would seem to require. We are changing our atmosphere in ways that will affect the planet for thousands of years, with no serious global mechanism for managing the process. We are building weapons capable of ending our civilization and maintaining them on hair-trigger alert, with command structures that rely on the consistent good judgment of an unbroken chain of human beings across decades and centuries. We are developing biotechnologies and AI systems faster than the governance frameworks that would manage their risks are being built. This is not a political argument for any particular policy. It's an observation about the gap between the scale of what's at stake and the seriousness with which we're treating it. If the universe has 1 million civilizations and we're just one of them, our failure, if we fail, is a tragedy. But if we are actually the only witnesses the universe has ever produced, if we are the single place where matter became aware of itself, then our failure would be something more than a tragedy. It would be an event with no analogue in the history of the cosmos. The universe would go back to doing what it does without any awareness of itself. The stars would keep burning, black holes would keep swallowing, galaxies would keep colliding. But the watching would stop, the asking would stop, the wondering would stop, and that silence would be different from the silence that preceded us, because the silence that preceded us was just waiting. The silence that followed us would be, simply, the end of something. I don't say this to be dark. I say it because I think it's actually the most motivating thing I know. We are here, right now, asking this question, aware of our own existence in a way that nothing else in this galaxy, as far as we know, has ever been. That's not a small thing to be. It's not something to take lightly. It's the most extraordinary circumstance I can imagine being in. Let's end by pulling back to the widest possible view. We started tonight by saying that the question of whether we're alone is something most people think they understand but don't. I hope by now you see what we meant. The question is not simple. It's not answered by the size of the universe. It's not answered by the number of stars or planets. It depends on factors we don't know and measurements we haven't made. It lives at the intersection of astronomy, chemistry, biology, philosophy, and what might be the most personal question any of us ever sits with: does any of this matter? We've covered a lot of ground. The Drake equation and its honest unknowns, the Fermi paradox and the specific strangeness of the silence, the rare Earth hypothesis and its long list of improbable conditions, the Great Filter and its 2 terrifying possibilities, the zoo hypothesis and why it probably doesn't hold together, the dark forest and why it's disturbing even if it's wrong, the virtual transcendence hypothesis and the haunting possibility that intelligence goes inward rather than outward. The biosignature search is underway right now, and the telescopes being built to do more of them. The near misses, the named individuals who stepped between humanity and its own worst instincts, and what their existence tells us about how much luck is involved in getting this far. And we've walked back and forth between the cosmic and the personal, because that's where this question actually lives. Not in the stars alone, in the stars and in us, simultaneously. Here's what I keep coming back to. Whether we're alone or not, whether the galaxy is silent or whether it's full of quiet conversations we're not yet sophisticated enough to overhear, we are unambiguously here. We arrived. Something happened on this planet, in this solar system, in this small corner of this particular galaxy, that produced beings capable of asking exactly these questions. The fact of that arrival is not small. It doesn't need the company of other civilizations to be significant. It's significant on its own terms. What we do with it, what we build, what we survive, what we understand, what we pass on, is entirely up to us. That's not a reassurance. It's just the truth. And the truth, even when it's heavy, is better than a comfortable story. Better than filling the silence with voices we've invented so we don't have to sit with the silence itself. The sky is quiet. We've been listening. We keep listening. And we ask the question again tonight, as we've asked it since the first human looked up at the stars and wondered, is anyone out there? We don't have the answer yet, but we have the question, and we have each other here on this small, warm, improbable planet, asking it together. If tonight left you sitting with more questions than answers, that's exactly where it should leave you. The next video right here goes even deeper into what the James Webb Space Telescope has actually found in its first years of operation, and why some of those results are changing what we think we know about how planets form and what they might contain. We'll see you there.